Here is return from the radiator, goes into the reservoir, and this allows for expansion. So we come out of the reservoir, go through this little pipe adapter thing so it doesn't kink. So we go from the reservoir to the pump, just as I did on the board. This is a high flow pump. So reservoir, pump, and from the pump it goes up, and I have a cool flow meter so you can actually check how many RPM it's going and see the actual liters per minute, but that's not necessarily necessary. Not necessarily necessary. Anyway, so it goes up here. This is the positive flow of cool water. It splits 4 ways. First path we're going to look at is right here. It has this thing on it because the hose kept collapsing on me. So it goes here. Here's those voltage regulators that we were talking about, because they like to get really, really hot. So we hop from one chain of voltage regulators to another chain of voltage regulators. Again, to equate this to a circuit, is we have one primary power bus, then we split into 4 parallel circuits. Inside those parallel circuits, there's stuff in series, then they all come back together to a centralized power bus. Electrical metaphor there. So we come out of the voltage regulators, go back here, and you go to one of those bag things behind the motherboard. Then out of the motherboard, out of that, we go back to this recombiner system, which sends it back up to our radiator. Now we're going to follow the next path. This one goes from the cool supply over here through the north bridge. Now, it doesn't just go through the north bridge, because there's actually a special plate underneath all these video cards. So the north bridge is right here, and our south bridge is hiding under all the video cards. There's actually a special plate that takes the water from this pipe and sends it all the way down across all the components along the bus that connects the north and south bridge, and hits the south bridge with cool water and brings it back up. Coolant's custom made it for this motherboard from ASUS. So then out of the north bridge and south bridge cooler, come up into your top GPU. It goes out around, like say here's the GPU, it goes around, hits all the RAMs, comes back, does the CPU, and then back out. Then it does that in series with the next 3 there's 3 GPUs total, does those in series, comes back down here to the combiner where it puts the hot water up again. Now for the most important one, right here to the CPU. Comes straight to the CPU from the cold supply, out of the CPU, straight up to out. Just one thing on the CPU. The really hardcore guys have an entirely separate radiator, entirely separate reservoir, and entirely separate water pump just for the CPU. This is limited at about 4.15 gigahertz per core, where I have it right now, because of the fact the CPU will overheat if I put more voltage through it, because I have it all on one loop. My objective here was to have a mobile desktop that I could take here. The other guys have external radiators, and it just seemed ridiculous to me, so I wanted to put everything inside. So consequently, I paid the price of having 4.15 gigahertz instead of like 4.6 gigahertz. I can live with that. The final...
You said that was per core?
Per core. Oh yeah, so
your computer is like 12 gigahertz.
If you want to think about it that way. But something I forgot to mention is Pentium 4s had hyper-threading. For those of you that remember that, before they came out with dual cores, it's a system where you can run 2 threads on a physical core. They killed that in the Core 2s to make it cheaper to manufacture. They brought it back in the i7s. So the i7s have 4 cores with hyper-threading on top of each core. So effectively you go in the Windows and it shows up as 8 cores. So it effectively performs, hyper-threading allows it to perform 25% better than if it was just 4 cores. So it effectively performs like 6 cores at 4.15 gigahertz, which is ridiculous. Anyway, so we have cold water here. This is the last and final loop. Cold water goes into the hard drive coolers, and from there we go somewhere into the RAM coolers, which are hidden back here. Then from the RAM we go out, up through here. Here's the temperature sensor, and here's our 4-fan radiator at the top. Now, you got to make sure you have a gigantic radiator, because the only disadvantage to a big radiator is it's big. Everything about it is more efficient. You're going to pull that heat out of the water better. It's just better for the system in every way. So you want to have a gigantic radiator. Before this, we were requesting for a air spray can because you're supposed to clean your radiator all the time, and I hadn't been keeping up with it, so it was all clogged. You always want to make sure you got good airflow, because if there's no air moving, it's not cool. So before everybody comes around, look, don't touch for fear of static. Couple things is, before I said I used to fill this up all the way, which is a horrible plan. You'll notice a couple things around the RAM and right here, where the computer got hot one day in the summer and it started blowing coolant out of the weak spots in the seams because there's so much pressure built up from the high temperature water. Fortunately, it just leaked a teeny tiny bit and didn't hurt anything. I lucked out. Lesson learned, always leave a little bit of expansion space. There. Other thing is, if you're overclocking, you always need a high performance power supply, because your 16-phase voltage regulation for the CPU needs a rock solid voltage. And if your GPUs kick up and your power supply can't put out the amperage to supply the voltage regulators the proper input voltage, then your CPU voltage is going to dip and you're going to crash because you couldn't maintain that voltage you need for the higher frequency. So you want to get a gigantic power supply. Most computers in here probably have 200 watt power supplies. This is 1200 watt power supply, which when kicked up all the way with all three graphics cards going and the cores running when you're playing a new game, draws the equivalent of 14 amps at 115 volts from the wall. So you have to be very careful where you plug it in when you kick it all the way up, because it might trip it off. Other interesting fact is I tried 4 different power supplies when I was building this, and this is the only one that could actually work. Because when you're pricing out a power supply and looking at them, you want to look at the things called voltage rails. The cheap ones will have real high wattage, but they'll subdivide the current you can draw into like 6 subsections. And on each subsection you might be able to draw 12 amps. We'll say the idiot who wired it put a video card and a CPU on one 12 amp, and then 4 hard drive connectors on each one with their own 12 amp. Well, that makes no sense. That's the way the original power supply that I bought was like, because I didn't know what I was doing initially. So as soon as the video card would kick up, CPU didn't get enough voltage, the computer would turn off. Took me a long time to figure it out. This is from PC Power Cooling. They specialize in high performance industrial duty power supplies. They're rated to run at 105% capacity in a 120 degree ambient Celsius environment for 7 years. So I don't think there'll be any problems there. But the trick is, these use a single voltage rail. So this has 110 amp output on one 12 volt rail, which means any device on that whole thing can draw from that, and there's no limitations on what combination of devices. It's a vastly superior design. PC Power and Cooling uses it on every power supply they sell. They tend to be slightly more expensive than the competition, but if you're overclocking, especially with big video cards, you're going to definitely want it. Other fun fact is you can get coolant that's UV reactive, hence the black lights. So if I had the cover on, it was a dark room, everything would glow really cool. So now I suggest people come around, take a look. If you have any questions, let me know. I just don't want anybody touching anything for fear of static. The tubes are also UV reactive. They glow blue if there's no fluid.
You should put the cover on at the end. You can...
Yeah. So if anybody wants to come up close and take a look.
What brand is the motherboard?
It's okay.
Asus?
Yeah, it's Asus Rampage 2 Extreme.
Yeah, I noticed because of that.
Yeah. Oh, other fun fact: if you buy the high-end Asus boards, they have this little screen which gives you direct hardware access to information from BIOS. So you can have it tell you your voltages on the fly, direct, without any software intervention. You can control stuff from there. There's actually a little joystick on the motherboard where you can tweak voltages and stuff. Like, there's really hardcore stuff if you get the high gear from Asus. But this is really great because before the computer turns on, before you even see the power on self-test, it tells you what it's detecting and what error it hung on, and it gives you error codes which you can look up. So when you're overclocking and you put that base clock too high, the computer's not going to post, you're not going to get a picture, look at this little screen. It tells you exactly what's wrong and what you should change. It's invaluable when you're overclocking.
Yeah, I have the old version for AMDs, and the screen is actually in the back of the.
Yeah,
Yeah,
that's
you
how
have to
they
look
had
in
it
the back
originally.
end.
Yeah, I got one of those too. Like,
Yeah.
it doesn't actually work very well. Like half of them are always stuck on. But the printable is very good though.
Just have my name printed on it. It's pretty easy.
I keep temperatures on here normally
That's cool.
because the monitoring software doesn't play nice with Windows 7 yet. Yeah, so if you want to take a look at it, come up. If not, I'll go over the BIOS.